Hello everybody, and welcome to my talk about interactive C++ for data science. My name is Vassil Vassilev, and I'm a research software engineer with Princeton University. This is a pre-recorded talk, and I would like to answer questions at the end of it. Please use the Zoom system to ask a question at your convenience, and I'll make sure it gets answered. This talk is organized in 5 sections. An introduction, where we will discuss about some of the key insights of interactive C++, such as execution of statements, showing execution results, entity redefinitions, and how to recover from errors. We will take a look at interpreting C++ and existing tools and technology. We then will talk about interactive and interpreted C++ in data science. Then we will see uses of C++ in Jupyter Notebooks, how interpreted C++ and CUDA can be used for memorization of complex laser physics simulations. We will take a look at some of the use cases where eval-style programming is useful. We also show the root data analysis software package, which uses interactive C++ to process exabytes of data. In section 3, beyond interpreting C++, we show possible applications of having long-lived translation pipeline. We will see template instantiation on demand after the program was statically compiled. We will see how this can leverage on-demand technology for language interoperability. We will show several field-tested tools enabling automatic language interoperability with Python, D, or Julia. Section 4, interpreter or compile as a service. We try to put that work into context and possibly provide generic mental model to use when thinking about interpretative C++. We show how we can customize C++. We explain through examples how we can implement language extensions and offer application-specific code transformation tools. We argue that having a long-lived compilation pipeline, which can process C++ code incrementally, can provide efficiency and offer a lifelong optimization opportunities. Towards the end of this talk, we explain how we plan to make this work available in upstream LLVM. And since this is a pre-recorded talk and I can optimize my performance, there will be bonus content. I would like to show you how to instantiate and run a C++ template in a C program with less than 120 lines of code with the existing incremental compilation support in Clang. So let's get started. This talk is based on technology whose development started since 2010. It builds on experience in interpreting C++ gained since 1998. It would not have been possible if it weren't for the efforts of many individuals and organizations. This talk is about work conducted by me, but also the work of dozens of colleagues and contributors from many domains in science and industry. In the slides, I have tried to mention individuals and organizations where possible. Any characterizations, mischaracterizations, emphasis, and errors are solely mine and do not necessarily represent the views of other individuals or organizations. The current work is partially subsidized by the National Science Foundation. Let's get started. Despite the power of C++, it is often seen as difficult to learn, difficult to teach, and inconsistent with rapid application development or exploratory programming. Exploration and prototyping is slowed down by long edit compile run cycles during development. The goals of this talk are mostly to provide more information about the following questions. Is C++ a compiled language? Is C++ an expert language? In theory, the language translation should be an implementation choice. In practice, however, language design and evolution could affect the choice of translation, and the choice of translation can affect language design. What would it enable if we started interpreting C++? In interactive C++, shortens the compile run cycles and offers a different programming experience along with a better productivity in many cases. In this particular example, is adopted from YouTube video where the C++ interpreter Cling is used in the context of an OpenGL application. It becomes easier to orient a shape, select a color, and compare to previous settings. In particular, in the example, we spawn a visualization thread and interactively change the properties of the OpenGL objects. Then we join the thread and we exit. Exploratory programming or rapid application development is an effective way to gain understanding of the requirements for a project, to reduce the complexity of the problem, and to provide an early validation of the system design and implementation. In particular, interactively probing data and interfaces makes complex libraries and complex data more accessible to users. It is important in data science, computational science, and debugging. It significantly reduces the time consumed by edit run cycles during development. In practice, only few programming languages offer both a compiler and an interpreter translating them into machine code, although whether a language is to be interpreted or compiled should be a property of the implementation. Languages which enable interactive exploratory programming tend to have interpreters which shorten the compile run cycle, but this generally has a noticeable cost in performance. Language developers who acknowledge the use case of programming, of exploratory programming, may also put syntactic sugar, but that's mostly for convenience and thoroughness. The performance penalty nowadays is largely mitigated by using just-in-time or ahead-of-time compilation technology. For the sake of this talk, interpreting C++ means processing C++ incrementally, while mitigating the performance cost with JIT compilation. Interactive C++ means enabling exploratory programming for users, reducing the compile run cycles. There are several key insights about interactive C++. First, the incremental compilation. This assumes the C++ translation unit is ever growing, and multiple partial translation units can be added, similar to the namespace partitions. When used in interactive mode, invalid C++ does not terminate the session. Instead, invalid code is discarded. Incremental input consists of multiple C++ statements. C++ does not allow expressions on the global scope. An integral part of interactivity is printing expression values. Typing printf each time is laborious and does not naturally include the object type information. Instead, here, by omitting the semicolon, we request the last statement of the input to be reported as an expression result. Name redefinition is an important scripting feature. It also is essential for a notebook-based C++, as each cell is somewhat separate computation. C++ does not support redefinitions of entities. When the interactive system is embedded, it needs to communicate back and forth execution results. We can use placement new operations to memory given by the allocator or we can use an object which can do some basic lifetime management for us, like the value v in the example. The embedded system can access itself through its runtime. In this example, we can create a value object to store the execution result of the incremented variable I. V boxes the expression result, providing extended lifetime if necessary. This way, we can communicate expression values from the interpreter to compiled code. That mechanism can be used further to support dynamic scopes, extending the name lookup at runtime, as we will see later in this talk. Over the years, there were several systems which interpreted C++. CH, a proprietary cross-platform C and C++ interpreter and scripting language environment, originally designed by Harry Sheng as a scripting language for beginners to learn mathematics, computing, numerical analysis, and programming in C++. Its last release was in 2017. Sint, a command line interpreter, originally developed by Masaharu Goto and later included in the root data analysis software package, last released in 2013. Cling, an LLVM-based C and C++ interpreter developed in the field of high-energy physics to replace Sint in high-energy physics, in the high-energy physics package root. In this talk, we will be using Cling as a reference system for efficient and interactive incremental processing of C++. Let's take a quick data-driven view of how Cling works. The tool controls the input infrastructure by interactive prompt or by interface allowing the incremental processing of input. It sends the input to the underlying library of Clang, libclang, for compilation. Clang compiles the input back into AST and returns it back. When necessary, the AST is further transformed in order to attach specific behavior, for example, reported execution results or interpreted or other interpreted related features. And we get back an AST to send to libclang. Once the AST representation is ready, it is sent for lowering to the LLVM specific assembly format, the LLVM-IR. The LLVM-IR is the input of the LLVM just-in-time compilation infrastructure. Cling instructs the JIT to compile and run the specified functions, translating them into machine code, targeting the underlying device architecture, for example, x86 or NVPTX, which can run natively on the target machine. Cling was originally developed in the field of high-energy physics to enable interactivity, dynamic interoperability, rapid prototyping capabilities to C++. Cling supports the full C++ feature set, including the use of templates, lambdas, and virtual inheritance, and it supports the latest C++ standards. Cling adds a small set of extensions to C++ to allow interactive exploration and makes the language more welcoming for use. It compiles C++ code incrementally and relies on a JIT compilation. In that context, when we say that Cling is a C++ interpreter, we are not entirely correct. It is more like an incremental compiler with a JIT. This allows Cling to run on the target platform and still offer efficient code execution. Cling practically enables exploratory programming for C++. This talk will discuss some applications of interactive C++ developed to support data science researchers, in particular, interactively probing data and interfaces to make complex libraries and complex data more accessible. Over the last years, an ecosystem around interactive C++ has started to emerge. Let's take a few steps back, though. Although there is some disagreement about what should be the definition of data science broadly is the concept to unify statistics, data analysis, informatics, and their related methods in order to understand and analyze an actual phenomenon with data. Some consider it being the fourth paradigm of science, next to empirical, theoretical, and computational science. The definition of a data scientist is even harder for people to agree upon. It is roughly a person with a multidisciplinary background, usually in mathematics, statistics, and programming, who can analyze and interpret data. A data scientist can find patterns in complex data and understand their influence on some process. The advancement of the computational capabilities and machine learning gave a significant boost in the field recently. LinkedIn reports steady growth in data science jobs since 2012 by 650% on a yearly basis. The US Bureau of Labor Statistics sees strong growth within the data science field and predicts the number of jobs will increase by about 28% through 2026. And that is roughly 11.5 million new jobs. It is expected that the US will host around 50% of the data science jobs, which means another 11 million data science jobs will be emerging around the world. In terms of programming languages, the sources do not agree on the top 10 best programming languages and environments. One thing they agree upon is that Python has become the language of choice for data science. But also, C++ has its place in data science, being among the top 10 programming languages. Let's see several applications of interpreted C++ in science and industry. Jupyter Notebooks are becoming a standard for data science. The Jupyter Notebook technology allows users to create and share documents that contain live code, equations, visualizations, and narrative text. It enables data scientists to easily exchange ideas and collaborate by sharing their analysis in a straightforward and reproducible way. The programming style encourages notebooks to be organized in code blocks or cells, which can be re-executed. This makes Jupyter very welcoming to languages such as Python. Can it be also welcoming for languages such as C++? Jupyter's official kernel relies on Zeus, a C++ implementation of the kernel protocol, and the C++ interpreter Cling. Using C++ in the Jupyter environment gives a different programming experience. For example, we can use the visualization system to render rich content, such as images. But also, there is more advanced examples, such as rich rendering of math jacks using the sim engine symbolic computational library. In this example, we can see that the corresponding math expression, in their symbolic form. And interactivity, interactively we can ask for help. In this particular example, if we type a question mark before a C++ entity, we will get information from the relevant page. Of course, the possibilities are more than that. We can use visual widgets that are organized in controls, which provide user interface. In the example here, we create a slider around a value, and we can slide it and change automatically the value in memory, which then we can later use in other code. Another example, a little bit more complicated one, is that we can build an interactive geoinformation system where we can zoom in and zoom out and do things interactively. For more information about Jupyter and Cling, please check out Sylvain Corlet's talk from the Compiler Research monthly meetings. The Cling CUDA extension brings the workflows of interactive C++ to GPUs without losing performance and compatibility to existing software. To execute CUDA C++ code, Cling activates an extension in the compiler frontend to understand the CUDA C++ dialect and creates a second compiler instance that compiles the code for the GPU. In my view, here is also the beauty of the interactive approach. We can mix C++ and CUDA interactively on the target machine, and in theory, this gives us a better opportunity to optimize for the particular model of the accelerator hardware. And of course, this works in a Jupyter setup. In some simulation workflows, the system was used for memoization. There, using the interactive approach was useful to relaunch only partial part of the simulation from a given point. I will play a short video. You can find more details in Simeon's talk.
Both kernels supports the CUDA mode, so the kernel which is shipped with Cling and also the Xeus-Cling kernel. To enable the CUDA mode, you need to modify the kernel JSON file and add the argument -x to it to enable the CUDA mode. For the presentation, I prepared a small notebook to demonstrate you how we want to do our common workflow in an interactive way. On our institute, we have the laser plasma wake field acceleration simulation Picon GPU. Picon GPU is written in C++ and designed to run really well on big HPC systems. So for example, we executed on the whole Titan cluster on big partition of the Summit cluster. So Picon GPU can easily produce petabytes of data, which brings us some competition. On the one side, a single run can take hours. On the other side, we have problems to store all the data because most of the HPC systems cannot provide enough storage capacity. Also, it's a problem of the bandwidth to store all the data during the calculation time. In this, therefore, we want to use an interactive workflow. Normally, so means we want to do a live visualization so we can compact all the information in a small image and look if something interesting happens. And depending on what this happens, we want to stop the simulation, analyze it, and maybe change some parameters to change the way of the simulation. For this notebook, I don't use Picon GPU because it takes too much time. I use the game of life simulation to represent Picon GPU. So the idea is the same, just as a simulation. In the beginning, I prepare my simulation. So I include some headers and link also a library. So the libpng writer, this library is precompiled and I use it to generate the image. Then I define these helper functions. And here we have the CUDA kernels. The first one is a helper kernel, and the second one is the actual simulation kernel. For everybody who don't know is Game of Life. Game of Life is a stanza code which runs in iteration. So each cell has a state, dead or alive, and each iteration step it calculates the next state depending on the own state and the state of the neighbors. So it means the cell can keep dead or alive or become dead or alive. So I define the kernel, I allocate some memory. Here I define the initial word with a magic command. I write this word to a cell and you can see this mirrored L. I read the file, copy it to GPU and generate an initial image. Here's my main loop. I define 5 iterations which I execute, and with this cell I can visualize the simulation results in a nice animation. So the figure which I defined, this mirrored L, is called glider. And glider has a special ability. Each fourth iteration, it has the same shape on another position. So imagine on the simulation, maybe I see something interesting, so I stop and think, oh, now I should iterate maybe 3 iterations or. And so I define it and go back to my main loop. And now something pretty important happens. So if I execute my main loop again, I will not execute 8 iterations. I will execute only 3 iterations because I have the state of iteration 5 on my GPU memory. So for this small simulation, it's not so important. But you can imagine if I use Picon GPU, which produce petabytes of data, that could be 3,000 iterations until something interesting happens. And this can take minutes. Also, it could be possible that I miss the interesting point and need to go back or so. And therefore, I need to restart the iteration, and this can take incredibly long. So now I can do a small step to be sure and visualize it again. And you can see in the animation, it's iteration 8, and we have the mirrored L. So the other thing what I want to do is I want to do extra analysis. In my case, I want to call all living neighbors and visualize it in a heat map. Therefore, I use this kernel, which simply counts the living neighbors, allocate some extra memory on the GPU where I store the analysis result, execute the kernel, copy the data, define a heat map, generate the image, and display it. And if I compare it with the normal view of the simulation, you can see this is the point with the most living neighbors, and this is in the center of this L. And so, yeah, our simulation is true.
Another use case from data science is root. The main tool for storage, research, and visualization of scientific data in the field of the high energy physics. It is a specialized package, and it is a set of interconnected components that assist scientists from data storage and research their visualization when publishing a scientific paper. It is developed by the field of it is developed and maintained by the field of energy physics and organizations such as CERN, Fermilab, GSI, University of Nebraska, University of San Diego, and Princeton University. Last 5 years, root and Cling are used to store and process around 1 exabyte physics data, facilitating more than 1,000 scientific publications. Root uses Cling as a reflection information service for data serialization. The C++ objects are stored in a binary format vertically. The content of a loaded data file is made available to the users, and C++ objects become a first-class citizen. In practice, root heavily relies on eval-style programming. We use this to make it easy to inspect and use C++ objects stored by root. Cling enables root to inject names into the name lookup when a file is opened. Consider the following example. Here, n-tuple getTitle is unknown to the system, but then root stores C++ object in files. Here, as part of a single incremental input, we open a file called hsimple.root, and then we request getTitle for the n-tuple. It is still not known at compile time, and here we transform the unknown input into an eval operation. The eval operation includes some information about the surrounding environment, such as what is the expected return type, possible parameters, and other context. Once the file is opened, it becomes a name resolution resource, which can be used to dynamically resolve identifiers from. We can see that that file contains objects named n-tuple, and this is exactly what we talked about just now. But also, there is an object called hpx. The object hpx is of type th1f, which in root slang means a histogram. We can now just invoke the method on it and see the result being visualized on the screen. Then we can start to interactively adjust visual properties such as axes, legends, and so on. Root is a fundamental software for experimental physics and has been involved in many scientific breakthroughs, such as the discovery of the big void in the Khufu pyramid by observation of cosmic ray muons, or the observation of gravitational waves from a binary black hole merger by the LIGO experiment, and the observation of the Higgs boson at the Large Hadron Collider. To recap, we went over some basic and more advanced use cases for interactive C++. we saw that interactive C++ and incremental C++ can be very useful addition in some domains. I would like to make several takeaway observations here. Cling is not just a REPL, it is an embeddable and extensible execution system for efficient incremental execution of C++. It is used in several high-performance systems to provide reflection and introspection information. Cling can produce efficient code for performance-critical tasks where hotspot regions can be annotated with specific optimization levels. We will see more concrete examples in the slides to follow. Cling allows us to decide how much we want to compile statically and how much we want to defer to the target platform. Now we are heading towards several more advanced use cases of incremental C++. Imagine a system which can do pretty much anything with C++ at the runtime of your project. Can we connect such a system to other environments beyond C++? The usual way we teach two languages to talk to each other is by providing bindings. The bindings are utilities, usually implemented by library authors, to enable that crosstalk. A common way to use static binding generators such as Swig, zip, boost Python, pybind11 for Python, and say something like cxx-wrap.al for Julia. For instance, Swig and zip rely on limited C++ parsers, which need to be steered by yet another hard-to-use language. Advanced features are hard to support. And more importantly, it is up to your library author to provide such bindings. Alternatively, we could provide bindings on demand only for the parts of the library we care about. The approach is harder to implement, but it can support features such as template instantiations on demand. In the next couple of slides, we will take a look at how automatic language interop can be done to bind C++ with Python, D, or Julia. An example is CppYy, which provides automatic bindings for Python at runtime to C++ code through Cling. Python is itself a dynamic language executed by an interpreter, thus making the interaction with C++ code more natural when intermediated by Cling. It supports binding at runtime, template instantiation, function or function pointer callbacks, cross-language inheritance, automatic downcasting, and exception mapping. Many advanced C++ features as placement new, multiple virtual inheritance, and variadic templates work just straight out of the box. CppYy makes maintaining a large software stack simpler by using the provided reflection information by Cling, except for CppYy's own Python interpreter binding. It does not have any compiled code that is Python dependent. That is, CppYy-based extension modules require no recompilation when switching Python versions, or even when switching between CPython and the PyPy interpreters. CppYy achieved high performance through all lazy approach to runtime bindings construction and specializations of common cases through runtime reflection. As such, it has a much lower call overhead than, for example, pybind11. And looping over a SCD vector through CppYy is faster than looping over a NumPy array of the same type. Its implementation for PyPy, a fully compatible Python interpreter supporting a tracing JIT, can, in many cases, provide native access to C++ code in PyPy's JIT, including overload resolution and JIT hints that allow for aggressive optimizations. Of course, we need to pay the price of having an execution system in memory, which is approximately 100 megabytes. CppYy is used in several a large code bases in physics, chemistry, mathematics, and biology. It is readily installable through pip and through conda. For more details, check Wim Lovrijsen's talk in the link below. Another example is the Symmetry Integration Language, or SIL. It is a D-based domain-specific language of a functional kind, developed and used internally by the Symmetry Investments. One of the main goals of SIL is to be interoperable with all sorts of languages and systems, which is achievable through various plugins. To call C++ code, SIL uses a plugin called Xeus-Cling, which acts as a middle ground between SIL and Cling. However, Xeus-Cling does not interact directly with Cling, but through the cppyy backend, that is cppyy's C and C++ wrapper around Cling that provides stable C++ reflection API. Julia's on-demand interop package with C++ is called cxxjl. It takes a similar approach to cppyy, but it implements its own incremental compilation logic in its backend. One can conveniently switch back and forth between languages in the Julia REPL environment, but also C++ can be incorporated at runtime with Julia code. Julia can interoperate with non-trivial C++ code bases without previous preparation based on this technology. We saw a set of examples about how the incremental compiler can be used as a service by various applications. Let's see what compiler as a service actually means. The design of Cling is just like Clang, allows to be used as a library embedded in your code. In the next couple of examples, we show how to incorporate libcling in a C++ program. The program can be compiled by your favorite compiler. Cling can be used on demand as a service to compile, modify, describe, or extend C++, but also use CUDA. In the next slides, we will see how we can build binaries which use a compiler as a service to cross the compile time runtime boundaries. Let's consider the following example. We have a regular CPP file which creates an instance of the incremental compiler. Then we write a function at compile time that manages the interpreter object. The function then defines a function cube and compiles it at runtime. Note that we can instruct the system to spend more time optimizing the code if it was a hotspot. Then we take the address of the function which was compiled at runtime through the JIT. Then we cast it to a regular function pointer in the compiled code. And then we can use it just like any other function pointer call. Crossing the compiled interpreted boundary relies on the stability of Clang's implementation of the host application binary interface, or ABI. Over the years, it has been very reliable for both Unix and Windows. However, Cling heavily relies and is heavily used to interact with the GCC compiled code bases. And it is sensitive to ABI incompatibilities between GCC and Clang with respect to the Itanium ABI specification. Just like Clang, Cling can be extended with plugins. This means that our compiler as a service infrastructure can use domain-specific or application-specific extensions. This example demonstrates embedded use of Cling's extension for automatic differentiation called CLAD. CLAD transforms the Clang AST to produce derivatives and gradients of algorithms, as we saw in the talk from yesterday. When creating the Cling instance, we specify the -f plugin option in the path to the path to the plugin itself. In the particular case, we request from the compiler as a service to produce a derivative of function power of 2 with respect to x. This approach is particularly useful when power of 2 is a user-defined function or a template which takes user-defined types. Of course, since gradients and derivatives are used in high-performance computations, we request a higher level of code optimization because that would be a function that is executed often and performance matters. Like in the previous example, we get the produced function in our compiled code and use it. And here is also some candy. We can visualize the code which was used to produce the derivative of the value. Here, the getCode instruction also can print back the transformed code for debugging purposes. To draw the bigger picture, one can imagine the application development lifecycle. There is development phase, application deployment phase, application start phase, and application execution phase. The development phase has the constraints of writing software for an abstract machine and for some abstract user base. The more configurable the software is, the larger the user base it would fit to. That is one of the reasons to introduce software abstractions and indirections, such as configuration files. After development, at the process of deployment, things become very concrete. We need to develop the software, configure it, and start it and run it. The static compiler is the classical method to ensure efficient execution by encouraging, if not forcing, people to do as much as possible before deployment time. However, the constraints of being generic hinder some of the optimizations. There are more optimization opportunities in the compiler as a service land. Such opportunities can be after the binary is produced, at the point where it is installed and being configured. And this is called ahead of time compilation. After the binary is loaded by the system loader, or it is the just-in-time compilation. And while being executed, that is the continuous optimization time. For example, this is where we can JIT compile a given graph of functions with O0 to save startup time, and then, while executing, to recompile with O2 and swap the calls, just like the virtualization in a tracing JIT. The static compiler can defer operations to the compiler as a service, but that does not necessarily mean we need to be sacrificing performance. We may just want to reduce the binary size, avoid template instantiation explosion, or something like this. But also, the runtime can export information back to the other phases to optimize as necessary. In fact, the profile-guided optimization is such an example. We're working towards making the developments in Cling and the compiler as a service concept broadly available. In the context of the compiler as a service project, we're gradually making it possible to use incremental C++ in Clang. Nowadays, we can instantiate a template, execute it at runtime with around of 120 lines of code. I would like to show an example where a C program can instantiate a C++ template at runtime and call it. I have implemented a small library, a small shared library, which wraps the Clang interpreter library, lib interpreter, so that we can call it within C. If you want to know more details, please come to my talk at the LLVM developers meeting in a couple of weeks, and please also follow Lang Hams's org JIT v2 tutorial at the same place. We got a template called callMe in a struct B, which just print the type ID of its parameter. We want to instantiate it with a pointer to A. We need to find A to later create a parameter by calling the equivalent of new A. We find a class B, which contains the template callMe. Then we request the instantiation with the given parameters. Then we get the function pointer of the newly created compiled template at runtime, and then we ask the system to allocate memory on the interpreter side for A, which is the equivalent of making new A, open close parenthesis. Here, there are multiple ways to allocate memory, either on the compiled world side by calling the allocator and handing over the memory to the compiler as a service, or and then the compiler as a service will make a placement new, or just leave the compiler as a service deal with it. And finally, we can create, we can call the function pointer as we do usually in from what we saw in the previous slides. You can see that we can also slightly parameterize the example and pass random types at runtime for instantiation. And here, to conclude with the three initial questions. Is C++ a compiled language? For me, yes, it is, but it can be used in other ways differently. Is C++ an expert language? For me, maybe, but there are multiple ways how we can relax that. And what would it enable if we start interpreting C++? For me, it would offer a viable path to C++ from domains without extensive computer science background. For example, various sciences, data science, and it would generally relax the learning curve of C++. The approach can also enable performance, reduce binary sizes, and better compilation times. Thank you very much. And I have put some references where you can use to get more information about the kinds of work we're doing. Thanks a lot. We do have a bunch of questions in the Q&A box, so I will start reading them out loud and try to answer them. Keith is asking, can you please show the slide with the compiler on the left and the interpreter on the right? This one? So then, yeah, Kate, please ask your question. I would consider that answered. Is there a way to control optimizations and other flags that the compiler uses when compiling? It's a question asked by Andrew. So I think you mean the compiler as a service. In that case, yes, there are ways to control it. In Cling, we have several optimization levels. We have O0, which is the default one, because the trade-off is that if you are compiling with O1 or O2, things that are not on the hotspot of the computations, you're actually making the execution time worse. It's much easier to just run the code once rather than spending time to optimize it. But then for performance critical code, we can have like optimization 01, which is the equivalent of -01 for the static compiler, and 02, which is the equivalent of 02, and I think it goes up to 4. Now, what's interesting here is that we have several use cases where we want to enable specific optimizations, for example, loop invariant code motion or something else, so that it fits better the application domain. So we will be very soon working on this. And this way you will pick and choose your optimization pipeline. Of course, that comes with a caveat that some optimization may be not working well together, or some optimization combined in some odd way can do things worse. So it is an expert feature there. So it needs to match very well to the domain. I hope that answers it. Chuck is asking, Jupyter Notebook with C++ seems like a very effective tool for teaching C++. Do you find this combination makes C++ more approachable by novices? Yes, absolutely. So the Xeus-Cling development was actually contributed from the outside. So there is this company Quantstack. So they collaborated with some French university, and then the report by the French university using to teach Xeus-Cling, C++ with Xeus-Cling, essentially Jupyter through the Jupyter Notebooks, was very positive. So they run a course over a year with around 400 people, and then the lecturers were surprised because normally people would just lose interest in C++ because of the errors and stuff, but then with the Jupyter Notebooks, they just went off and then tried by themselves and then asked questions. So for them, it was a very positive experience, I would think. Kate is asking, do cloud services offer this service? Amazon, GCP, or Azure? No, that is not offered to my knowledge. So then there's a follow-up by Keith. Maybe Keith, we should talk about offline with that, but I'll just will read the follow-up. The compiler as a service would be method compilation, almost like Amazon Lambda service. I don't have extensive experience with the Amazon Lambda services, so I cannot comment. Chuck is asking, could continuous optimization be used to identify places where likely and unlikely attributes could be added to the static C++ files? Yes, and I think this is what essentially the profile guided optimization does. So there is this profile guided optimization where people normally compile their code bases with a special flag with a static compiler. Then they run a bunch of test suite or benchmarks which describe their workflows. And then they recompile given that information. So effectively what this does is it instructs the compiler to add likely or unlikely to the branches that are taken. So that is one case where the data information from the execution specializes the program at the static compile time. But of course, you can do more than that. In principle, you can instruct your JIT or just-in-time compiler to do things based on the previous runs. Also, the ahead-of-time compiler can do the same. So in practice, there the challenge is a little bit different because you don't have the source code. But then on the binary translation phase, where you have like some sort of an LLVM IR or some object which you can optimize upon, then you can make more aggressive optimizations which fit to your particular user base, to your particular domain, or to actually your particular set of users, because then the program can start optimizing itself for this particular use case, which I think is a very underestimated opportunity here. Andre asks, are these are there Docker Singularity containers with pre-built with Xeus-Cling and Jupyter Server? I think the Jupyter-Cling service is available through the Conda binary installer package. I am aware that there are a bunch of people that are using it within Docker images. I'm not sure whether there's an official one or something that's recommended. But just drop me an email or ping me offline. We can chat about that. Any more questions? I see there's some communication in the chat. No, there's nothing more. So unless there's anything else, it was fun talking to you guys, even kind of recorded and remotely. And I will hang around GatherTown for a while. So please come find me and then we can talk.